beginning part of the telecommunication, we're going to talk about amplitude modulation and frequency modulation, which is also commonly known as AM and FM. So, but before we start off with that, the first thing I want you to understand is that in wireless communication, how does it actually work? So you want to transmit an information, and let's say that's a speech signal. So a sound signal would arrive at a microphone, and that microphone, with the use of the piezoelectric crystal, would convert that sound signal into the electrical pulses. These electrical pulses are being transmitted to the antenna or the area, where because of these alternating compressions and rarefactions, definitely an alternating current would be produced in microphone. And when that alternating current reaches the transmitting area, the electron oscillates. And as electron oscillates in the transmitting area, it produces electromagnetic waves. And these electromagnetic waves travel to the receiving area, where they produce an effect which is similar to electromagnetic induction. These microwaves will cause electrons to start oscillating here at the receiving end, and that will produce a current. You would be using operational amplifiers over here, both at the transmitting end and the receiving end, to amplify the signal. And then that would be fed into the loudspeaker, where the loudspeaker would convert that back into the sound signal. So guys, the other thing you need to understand is that you can sort of correlate this concept a bit with transformers. There is a big difference, but even in transformers, you would notice that there is a primary coil and there's a secondary coil, and there's no physical connection between primary and secondary coil. An alternating current in the primary coil would produce alternating magnetic field, and those alternating magnetic field would induce EMF in the secondary coil, and that will cause current to flow. So this effect is similar to that. Only difference is that in transformers, you try and keep those pair of wires as close as possible, because you want maximum efficiency of power to be induced in the secondary coil. Here, you want to transmit information as far as possible. So you keep them as far as possible, and so that still a receiving antenna could detect the signal. And this works on the basis of resonance. So when a particular signal is being transmitted and it needs to be received by a particular receiving antenna, then in that receiving antenna, you already produce an alternating current whose frequency is same as the radio wave, so that the radio wave arriving would resonate the signal over here and produces a larger amplitude of oscillation. That's how it sort of receives its own particular signal. And that is something you might have noticed when you are in a room with, let's say, some other person who's also talking on a mobile phone, and you are talking on a mobile phone, but your signals don't overlap. That's because your mobile phone is operating at different frequency and the other person's mobile phone is operating at a different frequency. And since the two frequencies don't match, so hence there is no overlapping of signal. So each mobile phone would resonate with its own frequency signal. Now the thing is that whatever I told you might seem fine in the beginning, but in reality, that's not possible. It is not as simple that you have a sound wave coming to a microphone that would produce an alternating current. That alternating current would produce an electromagnetic wave, and then that electromagnetic wave would produce an alternating current in a receiving antenna. And the problem in this method of communication is all associated with the frequency of sound. Because the sound has a very low frequency, so the alternating current which will be produced has to be synchronized with the sound wave. So the frequency of sound wave would match the frequency of the alternating current. And if the frequency of sound wave would match the frequency of the alternating current, that would also match the frequency of the electromagnetic waves. So that frequency happens to be very low frequency for the electromagnetic wave. And low frequency would cause two problems. One is that if you recall the formula V is equal to F lambda, then with a low frequency, you have a longer wavelength. And there is a rule in telecommunication that the size of the antenna should be of the order of the wavelength so that it can absorb one signal at a time. So if frequency is very low, the wavelength would be really high, and that wavelength high would require antennas to be really long. That's almost like impractically long. So that is one problem with this low frequency. The other problem with the low frequency of the radio wave is that because it has a very low frequency, so it carries very little energy. If you know that a formula you did in AS in waves, that intensity is directly proportional to frequency square and amplitude square. So with low frequency, the intensity of the signal would be really less, and you have to rely entirely on the amplitude. And with low intensity, the signal won't be able to travel longer distances. That is also another problem, that with low frequency, the energy or the power carried by the signal would be really less, and hence it won't be able to travel long distances. And guys, there's a third problem as well. The third problem is that there will be, if you talk about using the frequency of sound waves, so generally the sound waves have frequency in a very short range, very similar to each other. So if you have to set up two radio stations, you won't be able to do that because both radio stations would be working at nearly the same frequency. And if both radio stations are working at nearly the same frequency, then their signals would overlap with each other. And hence you won't be able to operate with more than one radio signal or more than one radio station. The problem with low frequency is being solved by modulation. And there are two types of modulation techniques. One is amplitude modulation and the other one is frequency modulation. Amplitude modulation is more of an older technique and frequency modulation is more of a newer technique, where you would be able to choose frequency of transmission irrespective of what is the frequency of the signal. Despite the fact that signal has very low frequency, you can choose the wave that you send of your very own frequency. So there is one signal that is a signal that needs to be sent. And as I told you that there are two types of modulation techniques. So let's first focus on amplitude modulation. In amplitude modulation, if you have to send a signal with a certain frequency, you put the signal onto the carrier wave of its own frequency. So you can choose what carrier wave you want. You might have heard of AM 80, AM 81, AM 82. These are the frequencies. AM 81 is 81 megahertz. Then you might have, I think you might not have heard of AM, but you might have heard of FM for sure. At FM 100, FM 101, FM 102. So this is 100, 101, 102 are the megahertz of frequency. So that's the frequency of the carrier wave that you choose. How are you sending your information on the carrier wave that you choose yourself? You put the information In case of amplitude modulation, we put the information as an amplitude of the carrier wave. So in amplitude modulation, the amplitude of the carrier wave varies in synchrony with the audio signal. When audio signal is high, the amplitude would be high. When audio signal would be low, the amplitude would be low. So as the audio signal varies, you choose you're gonna send a carrier wave of particular frequency, then you vary the amplitude of the carrier wave in synchrony with the audio signal. Higher amplitude with higher signal and lower amplitude with lower signal. So as part of your transmission system, you will have two more components. One is modulator on left hand side, and the other one is demodulator on the right hand side. There's going to be a modulator attached over here, and there's going to be a demodulator. So what modulator does is that it analyzes the audio signal, and it has already a set frequency of transmission, and it changes the amplitude of the carrier wave in synchrony with the audio signal. So the signal that goes through is not this. Is of course not this. This is the one that goes through, where you have chosen frequency of your own choice, but the information lies in the amplitude of the signal. When it arrives, the signal is made to pass through a demodulator, where it would analyze it again, and for low amplitudes, it's going to produce a low displacement signal. For high amplitudes, it's going to produce a high displacement signal. So this signal is being reproduced by the demodulator. So you're not transmitting this signal. You're transmitting this information, where the information of your original signal lies in the amplitude, where demodulator would put it back into that form before passing it on to a loudspeaker. And guys, in frequency modulation, the frequency is made to vary in synchrony with the speed signal. So there's going to be an original signal, and with that original signal, you have to send it through a particular specific carrier wave. In frequency modulation, the frequency of the carrier wave is made to vary in synchrony with the speed signal. So where speed signal is high, you make a wave with a higher frequency. Where the speed signal is low, you make a wave with a lower frequency. So this is what's being transmitted through. Higher signal means higher frequency, lower signal means lower frequency, and higher signal means higher frequency again. So this is what's being transmitted. It's transmitted at a range of frequencies, but somehow this information is being transmitted with the main original carrier wave frequency, which is the frequency I was talking about. If the radio station is FM 100 megahertz, so this carrier wave will have 100 megahertz frequency. And when you put the signal onto that carrier wave, this is being transmitted through. What puts the signal onto the carrier wave is called modulator. When it arrives at the other end, there would be a demodulator. It would analyze the receiving signal, and it will reproduce the original audio signal by analyzing where the frequency is high. It produces a signal with the higher displacement. Where the frequency is low, it produces a signal with the lower displacement. So in frequency modulation, the frequency of the carrier wave is made to vary in synchrony with the original audio or speed signal. Guys, I would want you to know that one question that examiner can give is that he can just give you these two graphs, the top one, and will ask you to make the modulated carrier wave. So you just have to keep that thing in mind, that you will make the modulating carrier wave by identifying that where the signal is high, the amplitude would be higher. Where the signal is low, the amplitude would be lower. So, I mean, you're going to do a more fair work, but what I want you to understand is that you'd first make the wave envelope. Where the signal is low, there's going to be lower amplitude. Where the signal is high, there's going to be a higher amplitude. So after you make a wave envelope, you would fit in the constant frequency inside that envelope. So my diagram is not very accurate, but in exam when you're doing it, you are supposed to make it more accurate. And the other thing I want you to identify is that examiner can give you this graph and would ask you to reproduce these graphs. So with this graph, you can find out the time period and hence the frequency of both the carrier wave and audio modulating signal, because the size of each small wave has remained unchanged. So if you read the time period of this one small wave, that would be the original time period of the carrier wave, because the frequency of the carrier wave hasn't changed. And you can use that as 1 over time period to calculate the frequency of the carrier wave as well. And you can also make the carrier wave if that's not given to you by looking at this graph. Likewise, examiner can ask you to find out the frequency of the modulating wave, modulating audio signal out of this diagram. So you can see one wave from here to here. That's one audio signal. So that would be the time period, and hence you can identify the time period and make a sketch of a modulating audio signal. So what I'm trying to say is that with these two diagrams, you should be able to make this. And with this diagram, you should be able to make these two as well. Now this one's a little harder to make, but you can still see that where the signal is high, you produce more waves which are very closer together, and where the signal is low, you can produce waves further apart, and that's how you can make a frequency modulated wave. So you can't make this very accurate, but with these two being given to you, you can make a sketch of this. And with this being given to you, you should be able to figure out these two as well. And now that's a little tricky thing. The reason for that is that, guys, if I look at this particular wave and I want to make judgments about the carrier wave and the modulating audio signal, then I would know that right from a middle of compression to the next compression is going to be one audio signal wave. So I can read that time from the horizontal axis, and that time would become the time period of the audio signal. And hence, I mean, I can read time period, I can make a graph, and I can also determine the frequency of the original modulating audio signal. Reading a carrier wave frequency is a bit of a tough one because the time period of the carrier wave has changed. So how do you read the time period of the carrier wave? What you're going to do is that once you have read the time period of the audio signal, that's from middle of compression to the next compression, then you count how many waves are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and let's say 12. So if you divide this whole time by 12, you'll get on average the time of one carrier wave, because at some point it has become more, at some time points it has become less. So you see, there are points where the time period of the carrier wave has become more, there are points where the time period of the carrier wave has become less. So if you do the average, that is total time of one compression to the next compression divided by the number of waves, you get the average time of the carrier wave, which will be equal to the time period of the original carrier wave. And hence you can read the time period of carrier wave and use that to determine the frequency of the carrier wave as well. So where the signal is higher, the frequency would have increased. Where the signal is lower, the frequency would have decreased. But right below the point where the signal is 0, the frequency would still be the same. So I could also read the time period from here of the carrier wave, which would be unchanged because the original signal is 0, and the amount of change in frequency corresponds to the amount of signal. But this is an alternative way of doing it. So guys, there are certain advantages of frequency modulation, and there are certain advantages of amplitude modulation. But you need to identify that frequency modulation is more advanced technique, and hence it has a better quality, generally speaking, but it is also not very cost effective. So we have to explore the reasons for that. The first thing that you need to identify is more of your, I don't know, I mean, if you might know of it, or you can ask probably your parents about it, then they would tell you that AM is generally used for match commentaries or for news broadcasting because they're very cheap and they don't have very good quality. Whereas frequency modulation is something you might be aware of yourself, is used for music transmissions where you want the quality to be better. So it's very, very obvious that frequency modulation has a better quality. So guys, why frequency modulation has a better quality? One thing that I just told you, which was part of our syllabus, that what is the bandwidth of amplitude modulation. So similarly, bandwidth of frequency modulation can be determined based on what waves are being added to produce the frequency modulated envelope. But the bandwidth of frequency modulation happens to be quite bigger than the bandwidth of amplitude modulation. So if its bandwidth is bigger, then it has more range of frequencies. And something that works with more range of frequencies should be able to produce better quality of signal because musical instruments have range of frequencies. So having a larger bandwidth is an advantage for frequency modulation because frequency modulation works with a larger range of frequencies and hence it can produce sound signals with a larger range of frequencies as well, and hence it gives you a better quality of sound. The other reason for frequency modulation had to have a better quality is because you know that whenever an unwanted interference would add, it would add to an amplitude or displacement. So if this signal is transmitted and some random power gets added, that would get added to the amplitude and that will distort the information because information lies in the amplitude. But in frequency modulation, even if some unwanted power gets added to the amplitude, it won't be a problem for us because the information lies in frequency, which wouldn't get changed. So even after traveling a long distance and adding of unwanted external interference, the frequency modulation would still carry the same information, but the amplitude modulation would not carry the same information. So we just talked about the advantages of frequency modulation. There are advantages of amplitude modulations as well. Amplitude modulation has cheaper circuits. So if you want to make an amplitude modulation circuit, the circuit components required are less complex, less complicated, and hence it's very, very cost effective. And because they have a shorter bandwidth, so they occupy a smaller range of frequencies. And since they occupy smaller range of frequencies, you can set up more radio stations. Like for example, you have a 20 kilohertz range of frequency available. If AM has a bandwidth, if FM has a bandwidth of 170 kilohertz, then since you require 200 kilohertz to set one radio station, so you would be able to set up only one radio station in that available range of frequency. If you want to set up an amplitude modulation station and has a bandwidth of 30 kilohertz, so with a range of 200 kilohertz, you can set up 200 upon 30, which is like 6 radio stations. So that's also an advantage. And with amplitude modulation, you can, with the available band of frequencies, you can set up more radio stations in amplitude modulation as compared to frequency modulation. And guys, the last advantage is a very, very interesting and amazing one. You know, you would want or you would expect frequency modulation to travel longer distances because you're using higher frequency, and hence with higher frequencies, they would be able to carry more energy and they would have be able to travel more distances. Yes, that's right. It travels more distances, but it travels the distances in the line of sight. So it just moves out in space. So if you want to operate between two stations around the ground, the curvature of Earth will obstruct the signal reaching to the other point. So the frequency modulation signal would be working in a very short range of distances. So you need to set up repeating stations at regular intervals for frequency modulation, despite the fact that they travel too far away, but they travel too far away in space. So you can't do ground-to-ground communication because the curvature of Earth would obstruct the signal from traveling from one point to the other. But amazingly, that doesn't happen in amplitude modulation. And that's because above the Earth, you have a layer of ions, which is called ionosphere. So that amplitude modulation signals carry such little energy that they can't penetrate through the layers of ionosphere. So they keep reflecting back from the ionosphere, and hence they can travel more distance along the Earth's curvature. So it has from point on Earth to another point on Earth, AM has a longer range of transmission. So you can transmit information through a longer distances with the help of amplitude modulation. So like with one transmitting station, you can also operate throughout the country. And telling you from my experiences, I mean, sometimes it has happened to me that I'm tuning into a AM radio station to probably listen to some commentary of a match while in car. I have tuned to some radio station whose language even I can't recognize. So that means I am receiving signals from other countries. That's again because of the fact that AM signals travel through longer distances. But for FM, you even might have noticed that different cities have their different FM radio stations because it can't travel through longer distances.